In this deck, we focus on automated gate operations as both an efficiency lever and a safety critical system. Automated gates are the first line of control for vehicles and personnel entering and exiting a facility, and they rely on sensors and automation logic that must work reliably under continuous operation. The central problem is to monitor sensors and detect damage early so you prevent failures before they cause downtime or incidents. But monitoring and maintenance are not free. The system must minimize monitoring cost and downtime cost while improving safety and availability. That means choosing what to monitor, when to maintain, and how to respond to early warning patterns. Consider a major distribution center that processes 2,000 truck movements per day through multiple automated gates. Each gate uses a sensor array that can include photo eye sensors, ground loop detectors, magnetic inductance fields, and safety beam systems. The facility operates around the clock with minimal human supervision, so predictive maintenance and automated damage detection are essential. Reactive maintenance is expensive and risky. The scenario highlights average downtime costs of $15,000 per hour. The operational goal is to detect problems early and schedule maintenance proactively so gates stay available and safe. We solve the problem through a tiered toolkit that moves from rigorous optimization to scalable and human-centered operations. Tier 1 provides a mixed integer programming formulation to optimize monitoring and downtime trade-offs. Tier 2 uses a priority-based greedy heuristic for real-time monitoring decisions. Tier 3 applies ant colony optimization to discover better monitoring patterns over time. Tier 4 uses reinforcement learning, specifically a double deep queue network approach, to learn context-aware monitoring policies. Tier 5 integrates decisions into a digital twin for system-wide simulation and predictive maintenance. Tier 7 frames a human and artificial intelligence partnership supported by explainable reasoning. Tier 1 builds a formal optimization model that decides what to monitor over time and links monitoring decisions to failure detection and gate uptime. A key point is that downtime cost depends on demand. When a gate is down, vehicle arrivals amplify the economic impact. The formulation also tracks sensor health as a health index that degrades when failures occur and can be restored through maintenance. This turns maintenance into a decision lever. Instead of waiting for breakdowns, the model uses health signals and failure logic to plan monitoring and maintenance in a cost-effective way. This slide defines the sets that structure the model. You have a set of gates, a set of sensor types, a set of time periods, and a set of failure modes. Operationally, these sets make the model interpretable. A decision is always tied to a specific gate, a specific sensor type, and a specific time period. Failure modes represent the ways things can go wrong, which helps connect monitoring decisions to real failure risk. Parameters describe costs, failure characteristics, and demand. Monitoring cost captures the expense of monitoring a sensor at a gate. Downtime cost represents the economic penalty when a gate is not operational. You also have failure rates that vary by gate, sensor, and failure mode, plus detection times that represent how quickly a failure can be observed after it begins. Maintenance intervals and demand levels complete the picture. Demand is critical because it scales the damage of downtime. The same failure is far more costly during peak arrivals than during quiet periods. Decision variables represent what the system chooses. The model selects whether a given sensor at a given gate is monitored during a given time period. It also represents whether a failure mode occurs, whether the gate is operational, and what the sensor health index is over time. Operationally, the health index is a compact way to summarize degradation. It gives the model a memory of wear and stress rather than treating each time period as independent. That is what enables predictive maintenance planning. The objective combines two cost streams. First is monitoring cost, which grows with how many sensors you monitor and how often. Second is downtime cost, which occurs when gates are not operational and is amplified by demand. The trade-off is fundamental. If you monitor too little, failures go undetected and downtime explodes. If you monitor everything at all times, monitoring cost becomes excessive. The objective forces a balanced policy that spends monitoring effort where it prevents the largest downtime impact. This constraint enforces that each gate must have at least some monitoring coverage in each time period. Operationally, it prevents a dangerous corner solution where the model reduces monitoring cost by monitoring nothing. Even minimal monitoring coverage provides baseline visibility and ensures that critical failures have a chance to be detected. This constraint links monitoring decisions to failure detection. A failure can be detected only if the relevant sensors were monitored at the right earlier time, accounting for detection delay. Operationally, this is what makes monitoring meaningful. It captures the idea that detection is not instantaneous, and that missing monitoring at the wrong moment can let damage progress silently. This constraint links gate uptime to failures. If a failure occurs, the gate may not be operational. Operationally, this connects technical faults to service outcomes. A gate that is down creates queues, causes delays, and can force rerouting. In safety-critical environments, it can also create hazardous conditions if safety sensors fail. This constraint models how sensor health changes over time. Health degrades as failures occur and can be restored through maintenance actions. Operationally, this captures real wear and tear. Sensors do not fail only as random one-off events. They degrade under repeated stress, environmental exposure, and mechanical wear, so maintenance should be scheduled before health drops into a risky region. This constraint keeps sensor health within valid bounds from 0 to 1. Operationally, bounds prevent impossible states such as health greater than 1 or negative health. It keeps the model consistent and ensures the health index can be interpreted as a normalized condition measure. This slide shows a node-based diagram representing gates, sensors, time, and failure interactions. Use it to see the structure of cause and effect. Monitoring decisions influence detection. Detection influences whether failures are recognized in time. Failures influence gate uptime, and uptime influences cost through demand. Driven downtime impact. This example considers a facility with 2 gates and 3 sensor types over a 24-hour period. Peak demand is 150 vehicles per hour at Gate 1 and 100 vehicles per hour at Gate 2. Monitoring cost is $5 per sensor per hour. Downtime cost is $15,000 for Gate 1 and $10,000 for Gate 2. With a failure rate of 0.02 for sensors, a representative plan monitors photo eye and safety beam sensors continuously and performs predictive maintenance for ground loops every 8 hours. The reported outcome is a total cost of $8,640 per day with 99.7% system availability. Tier 2 uses a greedy approach designed for real-time operation. The idea is to compute a priority score for each sensor based on criticality, recent failures, demand pressure, and environmental stress. Then, given a limited monitoring budget, the algorithm selects the highest priority sensors. This is practical when you have hundreds of sensors across many gates and need repeated ranking under changing conditions. The method scales well because it uses a priority queue, so updates are efficient. This flowchart shows the greedy loop under budget constraints. The system observes sensor conditions and failures, updates priorities, selects a monitoring set within budget, and then feeds new outcomes back into the next cycle. Operationally, this creates adaptability. When demand spikes, the algorithm automatically elevates priorities for main gate sensors. When failures cluster, it increases monitoring attention where risk is rising. In the first code section, you typically see how sensors are represented, how priority is computed, and how a priority queue is maintained. Operationally, the priority formula is the policy. It determines whether you treat recent failures as urgent signals, whether you prioritize safety beams over convenient sensors, and how strongly you respond to demand peaks. This section typically shows the selection step under a monitoring budget. The algorithm pops the highest priority sensors until the budget is exhausted. Operationally, budget handling is critical. If the system exceeds budget, it becomes infeasible to run. If it is too conservative, it may under-monitor and allow avoidable failures. This section usually contains the update logic. After a time step, you observe outcomes, record failures, update health estimates, and recompute priorities. This is what makes the approach dynamic. Monitoring is not a one-time configuration. It is a repeated decision under changing sensor health, changing environment, and changing traffic demand. This slide reports a simulation of a 4-gate facility over 48 hours with varying traffic. Example initial priorities include Gate 1 photo eye at 0.95 and Gate 2 safety beam at 0.87. With a monitoring budget of $200 per hour, the algorithm selects the top 3 sensors for continuous monitoring and achieves 94% system reliability while staying within budget. During peak hours, demand factors automatically elevate main gate sensor priorities, shifting monitoring effort to where downtime would hurt most. Tier 3 uses ant colony optimization to explore higher quality monitoring policies than a greedy rule can typically find. The decision space is modeled as a graph of sensor time choices. Artificial ants build complete monitoring plans probabilistically. Pheromone captures what worked historically, and heuristics capture current sensor health, recent failures, and demand. Local and global pheromone updates balance exploration and exploitation, so the algorithm can improve reliability and cost over time. This diagram shows ants traversing sensor time combinations and reinforcing successful monitoring patterns. Operationally, reinforcement means that if a certain pattern of monitoring repeatedly prevents costly downtime during peak hours, the algorithm learns to select that pattern more often in the future. In the first pseudocode part, you typically initialize pheromone levels and define heuristic desirability for monitoring choices. Operationally, heuristics should reflect real criticality. Safety beams and photo eye sensors often protect safety and flow, so they should become more desirable when demand or risk increases. This section usually constructs candidate monitoring plans. Each ant selects which sensors to monitor in each time period, subject to budget constraints. Operationally, feasibility must be enforced while constructing solutions. A plan that monitors more than the budget allows may look reliable but cannot be implemented. This section typically evaluates solutions and applies pheromone evaporation. Evaporation prevents the system from locking into an early suboptimal pattern. It preserves adaptability, which is important, because sensor risk and demand patterns can change across shifts and seasons. This part usually deposits pheromone based on solution quality. Lower cost, higher availability monitoring plans receive stronger reinforcement. Operationally, this is the learning loop. The algorithm continuously improves by strengthening patterns that prevent downtime at reasonable monitoring cost. This slide reports a case with 6 gates and 18 sensors over 72 hours. The method evolves from random policies with 85% reliability at $18,000 daily cost to optimized policies achieving 97.8% reliability at $12,450 daily cost. The reported emergent pattern is operationally intuitive. Photo eye sensors are prioritized during peak hours. Ground loop sensors are emphasized overnight, and safety beams are emphasized during shift changes when human traffic increases. Tier 4 uses reinforcement learning to learn monitoring decisions directly from interaction with a simulated environment. State includes sensor health, recent failures, time since last maintenance, demand level, and context such as time of day and day of week. Actions are binary decisions for each sensor, monitor or not monitor, constrained by a budget. The reward trades off monitoring cost, failure penalties, and uptime rewards. The goal is to learn a policy that spends monitoring where it prevents the most expensive failures. This slide emphasizes the reward structure. You pay a cost for monitoring, you pay a large penalty when failures occur, and you receive a reward when gates remain operational. Operationally, reward tuning determines behavior. If failure penalties are too low, the agent will under-monitor. If monitoring cost is too low, the agent will monitor everything. A realistic reward leads to a balanced policy. This slide specifies the constants used in the reward. Monitoring cost is 5, failure penalty is 1,000, and uptime reward is 50. The magnitudes express that failures are far more costly than monitoring. This matches real operations where downtime and incidents dominate cost compared to the small cost of sensing. This slide presents the neural network architecture used by the double-deep Q network approach. The key operational point is that the policy can learn complex, context-dependent decisions under budget constraints. Instead of a fixed rule, it can adapt monitoring intensity based on health degradation and time-of-day patterns. In the first pseudocode part, you typically define the environment, initialize networks, and set training parameters. Operationally, training is done in simulation because exploration in a live gate environment would be risky. The goal is to learn safely, then deploy a stable policy. This section usually covers action selection, with exploration and masking decisions to stay within budget. Operationally, budget constraints must be enforced in the action selection step. Otherwise, the agent will learn unrealistic behavior that cannot be implemented. This part typically shows how experiences are stored and sampled for learning. Experience replay helps stabilize learning and improves sample efficiency. Operationally, it allows the agent to learn from rare failure events without needing to see them constantly. This section typically contains the value update logic and the use of a target network. Operationally, stability matters. Gate monitoring decisions must be reliable. The target network approach reduces oscillation and helps the learned policy converge. This section often includes periodic evaluation and updating of the target network. Operationally, evaluation confirms that the policy improves not only reward, but real outcomes such as availability and avoided downtime under peak demand. This section typically manages training loops across episodes and handles episode resets. Think of each episode as a simulated operating period where sensors degrade, failures occur stochastically, and demand patterns vary. The agent learns to anticipate and act. This final part usually finalizes training and extracts the best policy. Operationally, deployment requires locking the policy and monitoring performance in production, with safeguards that allow fallback to conservative monitoring if anomalies appear. This slide reports training on a 3-gate and 9-sensor environment over 2,000 episodes. Average reward improves from about -200 for a random policy to about +850 for the learned policy. The behavior learned includes intensifying monitoring during peaks, scheduling maintenance in low-demand periods, and reacting to health degradation. The reported outcome is 96.5% availability with a 23% cost reduction versus fixed schedules. Tier 5 uses a digital twin to connect gate hardware, traffic systems, weather feeds, maintenance databases, and security systems. Real-time ingestion from more than 500 sensors updates a virtual representation that supports what-if analysis. Multi-fidelity modeling combines physics-based wear models with fast surrogate models and Monte Carlo and discrete event simulation, quantify risk and operational impact. Operationally, this allows the facility to test maintenance strategies and response plans before applying them. This slide emphasizes system of systems integration for predictive maintenance and scenario analysis. The key idea is that gate automation does not live alone. Weather affects wear, traffic affects demand, security incidents affect allowable operations, and maintenance capacity constrains what can be done. The twin integrates these couplings. This example describes a deployment with 12 automated gates and more than 600 sensors. A predictive model identifies an impending motor-bearing failure in Gate 7 with 89% confidence, 72 hours ahead. Scenario analysis suggests variable gate speeds could reduce processing time by 18%, while extending motor life by 23%. The twin simulates 10,000 scenarios to find speed profiles. It also finds an energy opportunity. Demand response integration generates $45,000 annually by reducing speed during peak electricity pricing. In security response, coordination reduces lockdown time from 15 minutes to 3 minutes while maintaining emergency access. Tier 7 frames the system as a partnership. Humans provide context, ethics, and stakeholder coordination. Artificial intelligence provides pattern recognition, optimization, and uncertainty estimates. Interfaces support augmented decisions with confidence intervals and drill-down explanations. Human feedback is used for continual learning and trust calibration, which is critical when decisions affect safety and security. This slide shows the Centaur workflow. Artificial intelligence recommends, humans decide, and the system learns from feedback. Operationally, this design prevents over-automation in high-stakes situations while still benefiting from computational decision support. This slide highlights the explainable components that make recommendations auditable. Operationally, explanations help operators understand why a sensor was prioritized, why a gate is flagged as high risk, and what trade-offs a recommendation is making between cost and safety. This incident example shows the value of collaboration. The system predicts a 73% probability of motor failure within 8 hours at gate 3. A VIP convoy arrives in 6 hours, so all gates must remain operational. The human asks a what-if question. What if we reduce gate speed by 30%? The system responds that failure probability drops to 23%, but processing time increases by 40%. The hybrid decision is to reduce gate 3 speed, activate backup gate 5, and perform emergency maintenance after the convoy. Post-incident learning stores the speed reduction strategy for future recommendations. This practice question asks you to formulate a 24-hour optimization for 4 gates and 3 sensor types under a $500 per hour monitoring budget. You use monitoring costs of 6, 9, and 7 per hour, and downtime costs of $12,000 per hour for gates 1 to 2, and $8,000 per hour for gates 3 to 4. You assume failure rates of 0.015 for monitored sensors and 0.045 for unmonitored sensors, and compute the optimal solution for the first 4 hours under uniform demand of 100 vehicles per hour per gate. This question asks you to implement the priority-based algorithm for 3 gates. Gate 1 has 5 failures in 48 hours. Gate 2 has environmental factor 0.8. Gate 3 handles emergency vehicles with priority 2.0. You use criticality weights 0.4, 0.3, 0.3, and a budget of $180 per hour. Then produce a monitoring schedule for peak hours 8 to 11 a.m. with full priority calculations. This question asks you to design ANT colony optimization for 5 gates with 15 sensors. You use evaporation 0.15, alpha 1.2, beta 2.5, and 25 ants per iteration. You analyze pheromone evolution over 50 iterations when gates 1 to 2 have failure rate 0.08 and gates 3 to 5 have failure rate 0.02, and estimate convergence and final pheromone distribution.